called the clean room. And as she already mentioned, we work in the clean room because we use special conditions. So as the name clean room suggests, we want to work in a clean environment, and the most biggest thing of this, we have the clean air. So we have air which we want to have free of any particles which will contribute on our sample. But it's not only the air we are controlling, so not only the amount or the density of particles, it is also stable air conditioning. So the temperature, because as she already introduced, the etching is strongly dependent on the temperature itself. So when the temperature is higher, and of course here in winter we have -5 and summer we have about 20, 25, and the temperature is higher, the etching rate is strongly higher. It means the process is working on different days in a different manner. The same with the humidity. The resist, which we are using to do the lithography, which is really the key process of all of we are doing, is strongly dependent on the humidity in the room. So we have to control temperature and humidity. But it's not only that, so there are also other substances. For instance, very simple, the tap water. The tap water includes metal ions, and those metal ions interfere with your surface. If you have a semiconductor, or if you have, for instance, a laser, and if the material of a laser, this can incorporate charges or defects which can, in the end, destroy the gain of your whole active material. So you have to be very sensitive. That's why also in the chemical lab we use deionized water, or as we call it, just DI. Okay, so let's get into it. So the problem is that in normal lab conditions, we can have contaminations which damage our micro or nano devices. So as Mr. Isaka already said, we are working in a range, in a feature size of between 10 nanometers to, let's say, 100 micrometers. If you now think about possible particles which would contribute, we can think about, for instance, the human hair. Has anybody ever of you worked in a clean room before? We saw it. You saw it from the outside, so from last Friday, so most of you were there. Last month. Okay, cool.
We didn't work, we just saw how they work.
Okay, you saw it from the outside, but you had never been into it. So you were already recognizing that there are special flows, for instance, and so on. So the reason is that all those particles, which are not really visible for the eye, they are so small, but they are still there, so they can contaminate our samples. So the human hair, for instance, when you do the microsystem technology lab, which I strongly suggest to do because we learn how the lithography process really works hands-on, then I also suggest you just put one of your hairs and put it under the microscope and just check what diameter you have. It's quite interesting. For me, since it's really simple when they compare it to other ones, so they can be up to 100, 150 micrometers. If you take a look at it. Dust particles itself, they are a little bit smaller. You can nicely see them when you would go to a scanning electron microscope, for instance, and you see your sample. Sometimes you think, oh, this is working really perfect, and then you put it into an SEM, and what you see is a lot of particles in them. And you're like, I cannot do an idea of it. So those are typically in the range of a micrometer. Then, if I speak, for instance, if I exhale, I have respiratory droplets, which are also in the micrometer range. Skin particles are usually a little bit bigger. And then, especially for smokers, but I would say in our generation it's again a little bit low. If you smoke, then you exhale a lot of particles. So there's even a rule in our lab that if you are a strong smoker, in the industry you're probably not allowed to smoke. But here in university we're a little bit softer. We say, okay, if you smoke, you have to wait half an hour until you can finally enter the clean room again, and you have to drink something before, so you don't exhale those particles, which would strongly influence the result of your lithography, etching, or deposition. this particle contamination leads to defects, and this is strongly happening in the lithography because you have to imagine what you showed already. We have a mask in lithography, so your particles act like this. So you have a masking effect, so you transfer what is this particle, you transfer onto your device. And this can lead to fatal defects, which we will see in a little bit later. But it's not only the particles, as I said, it is also the metal ions. That's why we aim, especially for clean water, filtered chemicals, and we have also to keep in mind that our tools are really clean. And we can have several others, chemical and biological contamination. The last point, again, really important, is, as I said, the temperature and the humidity conditions. This you really have to stabilize. So that's why when you enter our lab, for instance, and I think most of you saw it in the meantime, that when you enter the room, you have 3 control panels. So you can see the current temperature in the lab, so you can write down on your logbook what was the temperature in the lab today. You can write down the humidity, and see the resistance of the DI water. So if it's really deionized or not. So we measure the resistance, and with that you can know whether your process parameters or whether your process preconditions are really fulfilled, so you can start the process. Okay. When we then do our process, we need to somehow characterize our efficiency. So we introduce a parameter and we call it yield. So when I think about I have a waveform, I split it up into 1,000 different CPUs, which I would like to fabricate, and after fabrication, 100 of them fulfill my minimum requirements, and now okay, 100 out of 1,000 work. So the yield is just the ratio of this, which is 10%. We work in MEMS devices mostly. So when we have our MEMS device, we, let's say, fabricate 10 millions on a large scale. 8 millions of them work. We know 8 millions divided by 10. 80% is the yield. In university, the yield is not the most crucial thing, because we are mostly interested in the proof of concept. So when we fabricate 100 samples and 2 are working, and they show the proof, and they show this principle, and the proof of concept is fulfilled. But we have the same working in the industry. If your process yield is extremely low, and you have the same fabrication cost, then later your efficiency is too low to make the device price affordable at the later market. So when we think about now a simple model for the process yield, we can calculate with this, for instance, this equation. And this is now an example where we only take into consideration our lithography steps. Why the lithography steps? The lithography is the most prominent example for getting contaminations. There are mainly 2 reasons. So one, we have this masking effect where we can transfer directly on this on our substrate. And the second one is that the lithography itself is not done under vacuum conditions, for instance. So this process typically takes like an hour, 1 hour, and during this time, your sample is prominent to just ambient air. So you work with your sample, you put it on a hot plate. So there is a high probability that a defect can happen. So we count the numbers of our lithography steps. We have the density of other defects, which I will explain soon. And also interestingly, we have the area of the die. So for instance, the area of active medium range. So common sources for this fatal defects are, of course, the particle contamination, then the mask defect, which I explained, and of course, deviations of our process parameters. How could a fatal defect look like? So let's assume we want to generate this gray line as an electric electrical conductive line. So we want to later have here a metal. In this red area, this is our guarding area or our isolating area. If no particle comes, and we have to assume we have to do a lithography step to generate this, and it would just play here during lithography, then it is not interfering with the functionality of the line later on which we are fabricating. But if the